So let's look at building models out of linear functions. So with this, it'll depend on the information they give you in terms of the approach that you'll take. Sometimes they'll give you information about the slope and a coordinate, and you can use those two pieces together. Sometimes they'll give you two coordinates, you can use those pieces together. So let's look at those two types of examples. I changed this a little bit. I changed this value to 59,000 right here instead of 5,900 to make the numbers work a little bit better. Alright, so a town's population has been decreasing at a constant rate. So what this tells me right here is that we have a linear function because it's a constant rate. And what I also know is that we have a decreasing function. So when I get my slope, we should have a negative slope coming through. So that's what I can get out of that first sentence there. In 2010, the population was 59,000, and by 2012, it had dropped by 4,700 people. We're going to assume this trend continues. So, this one's giving me information about the slope right here. The fact that 2 years had passed and the population changed by 4,700. In fact, it dropped, so there's a decrease. So if I want to think about my slope here, it's the fact that I saw this drop of 4,700 people over 2 years. So what this will do is it'll give me the change per year by dividing these two values together. But you can think of it as well is if I have these two pieces, let's say my coordinates are made up of time and population. What this would do is the numerator is showing the change in population. So the fact that the population dropped 4,700 people over the change in time, which time increased 2 years. So it's just getting to a shortened version of that calculation without having to do any actual math to get there based on how they gave us the information. Okay, if we calculate that, that should be a negative 2,350. So there's this decrease of 2,350 people per year. So making my function, what we want to recognize is that they want us to have t in years after 2010. So this coordinate that I have here is actually the coordinate, if it's year 2010, then t is 0, and my output was 59,000. So what this gives me is the y-intercept. So my function will have our slope and intercept. So we'll have negative 2,350t, and then plus our starting population of 59,000 in 2010. So if I want to predict the population for 2016, well, that would come from thinking about 2016 minus 2010, so I get the number of years after 2010. So what I want to plug in is 6. So negative 2,350 times 6 plus 59,000, which will be 44,900. And then we make our sentence answer. So the predicted population for 2016 is 44,900 people. When will the population reach 0? So this is where we want P of t to equal 0, and then we want to find time. So I'm going to subtract 59,000 from both sides of the equation. Divide by negative 2,350. And that would give us t equals 25.11. So in terms of year, so we could say the population will reach 0 And you could round this to just 25. What you could also do is it's like between the 2 years, so between 25 and 26. So you could do that too. I'm going to use that idea. Between. So 25 years after 2010 is 2035. And then between 2035 and 2036 is when it will be 0. Alright, so there's an example where we have the slope and intercept, but the slope's given in kind of a different way where we have a little bit of calculation to do. Alright, given 2 points. So here we have in 1950, the median home value in Hawaii was $74,400. How nice. And by 2000, it was $272,700. Assume that the house values are changing linearly. So with that, we know we have a linear function to work with. So build a function of the median home value in Hawaii with regards to time, and for time we want in years after 1950. So what that tells me is I have this coordinate in 1950, time is 0, and the value was 74,400. And in 2000, which was 50 years later, so 50 years after 1950, 272,700. Alright, so for slope, we have 2 coordinates, so I'm going to calculate slope first and take the difference in the outputs over the difference in the inputs. And we'll just put that in a calculator, and that should be 3,966. And then, if we needed to, we could find the y-intercept by plugging in a coordinate. However, we already have the y-intercept. We're starting at $74,400. So with that, our function, which let's call this v of t, finding the home value given time, we'll have positive 3,966 t plus 74,400. Something I do here is just make sure that the slope makes sense. Like, that the fact that it's positive means the value is increasing, and that makes sense because we're seeing this increase in home value. Predict the home value in 2020. So this is where we're plugging in a time of 70. So we're looking at v of 70. So 3,966 times 70 plus 74,400. We could just plug that into a calculator to get 352,020. So the predicted home value in 2020 is $352,020. Alright, when will home values be over 300,000? So what we're doing here is this kind of the idea of an inequality. So 3,966t plus 74,400. And when is that going to be over 300,000? So we'd have the more than symbol there. So subtract 74,400 from both sides. So we have this 3,966t. We want that to be more than 225,600. Divide by 3,966. And since it's positive, our sign stays going the same direction. And we'll have t more than 56.88. So what we could do is round this. So this is giving us an amount of time. So it's like we're taking 2010, or sorry, not 2010, that was our last example, 1950, plus this 56.88. So home values will be over 300,000, and it's kind of happening during, like if we rounded that to 56, So 2006, it's happening in the middle of 2006. So what we could say is like after 2006 or starting in 2007. Say between 2006 and 2007. So up to you. Lots of choices for wording there. Let's go with after 2006. But you could have, like, if you rounded that to a whole number, it should round to 7. So if you answer this with 2007, that is absolutely correct too. It just kind of depends on your interpretation.